It's a pleasure to give a talk, this talk. Today I'll talk about exact phase transitions for stochastic block models and reconstruction on trees. So this talk will be about community detection. So let G be a large network or a graph with some community structure. So the easiest example to think of is the social network data where vertices are different people and edges encode whether these people are friends or not. And we wish to, given this graph, we wish to infer the community structure of these people. And also, J could be protein-to-protein networks. And the problem is, given this large graph G, infer the communities by partitioning the vertex set V. In this talk, I'll focus on the stochastic block model, which is a simple statistical model of a random graph with a community structure. So stochastic block model is a random graph with n nodes with q communities with parameters a and b. So for every node u, we independently assign a community or a label, sigma of u, 1 to q uniformly at random. So when q equals 2, this is just by flipping a coin and assigning the color blue or red to each vertex. And independently for each pair u and v, if they're in the same community, or either, in other words, sigma u equals sigma v, we include an edge with probability a over n. And if they're in a different community, sigma u is not equal to sigma v, then we include an edge with probability b over n. So if a is b, this is just a plain Erdős-Renyi random graph. However, if a is not equal to b, there is some hidden community structure that we wish to infer. So this block model has been studied in different communities. It has been studied by statistics community, and in the word stochastic block model came from this paper Allan, Lasky, and Leinhardt in 1983, and there's been hundreds of papers studying this block model. In the computer science literature, this block model is also called planted partition model. And it has been studied mostly from algorithmic perspective. Also, as I've mentioned previously, this is a natural generalization of Erdős-Renyi random graph, and it has been called inhomogeneous Erdős-Renyi random graph in the combinatorics literature. So before 2010, the theoretical analysis of the block model mostly focused on dense region, where a graph is connected with high probability. Then the interest is in recovering all nodes exactly. In this talk, however, we'll consider a sparse setting where theoretical analysis can be a little harder due to lack of concentration of the degree distribution. So if A and B is of order 1, the number of edges in this graph is typically linear in n. And the average degree is given by A plus Q minus 1 of B over Q. And I'll assume it to be greater than 1. Because if D is less than 1, all the connected components will be very small, and it will be impossible to infer the communities. So in this sparse regime, a linear fraction of the nodes are isolated. That is, they don't have any edges adjacent, and we can now hope to recover the communities of these isolated vertices. So the best hope is to recover a non-trivial fraction of sigma u. Okay. So this recovery is called a weak recovery. So note that if you have these blue labels and red labels, because the model is symmetric, we can permute them, and we will not be able to tell which is blue and which is red. So we only hope to recover up to a permutation of the labels. So up to a permutation, the question is, can we do better than random? That is, can we recover 1/q plus epsilon fraction of the vertices for some epsilon that does not decay with n. So this weak recovery is opposed to strong recovery, where one hopes to recover most of the vertices, and which is not possible in the sparse regime. One can also think of an easier task where one wished to develop a statistical test that distinguish this this block model with the random graph with no community structure, which is just the Erdős-Rényi random graph with n vertices and with connectivity probability over n. So the analysis of stochastic block model in the sparse regime was popularized mainly because of this seminal paper by Desal, Krasakala, Moore, and Zeborova. And this group of physicists made a very nice conjecture about the block model. And they had very convincing non-rigorous arguments and also convincing numerical experiments to support the conjecture. And so denote SNR by a minus b of square over q times a plus q minus 1 times b. So a minus b squared can be thought of as signal. So if a and b, if the difference is large, one can hope to recover the community easier. And q times a plus q minus 1 of b is just the degree times number of community square, which can be thought of noise. If there's a lot of degree and a lot of communities, it's harder to infer the communities. So this is really the signal to noise ratio, and their conjecture crucially depends on this quantity. So if SNR is greater than 1, they conjecture there is an efficient algorithm called leaf propagation, which weakly recovers the communities with high probability. If SNR is less than 1, the picture depends on the number of communities. So when the number of communities is either 2 or 3, they conjecture that the weak recovery and detection is information theoretically impossible. However, when q is greater or equal to 5, weak recovery and detection is solvable by inefficient algorithm, but not by an efficient algorithm. That is to say, there exists a statistical computational gap for when q is greater or equal to 5. So when q equals 4, the picture is more complicated. And this was conjectured by Richie Tersengi, Semerji, and Zeborova in 2019. So now the picture even depends on the degree of these problems. So if A is greater or equal to B, that is to say, within communities, there's higher probability of connecting, which is also called assortative block model. Or if A is less than B, called this assortative block model, and the degree being large, then it is conjectured that there is no statistical computational gap. That is, the information theoretic threshold is given by SNR equals 1. However, if A is less than B and degree is small, it is conjectured that there exists a statistical computational gap. And this SNR equals to 1 is called the Kesten-Stegun bound, coming from branching process theory, which I'll come back to in a moment. So after the seminal paper of Desal et al., there's been a lot of mathematical work verifying part of the conjecture. First of all, people have looked at the two community case where things are nicer, and this is completely solved. So Mossel, Niemann, and Sly in 2012 show that when SNR is less than or equal to 1, it is information theoretically impossible to recover the communities. And if SNR is greater than 1, two independent groups, Mossel, Niemann, and Sly, and also Mosselier, they show that there is an efficient algorithm that solves the weak recovery and also detection with high probability. And in general, irrespective of the value of Q, Abe and Stanton show that when SNR is greater than 1, there exists an efficient algorithm for weak recovery and detection. So on the efficient side, the conjecture is solved by Abe and Stanton. However, for impossibility results, much of the conjecture was left open. It is known that for Q greater or equal to 4, there exists some regimes of A and B such that information theoretic threshold is less than the Castanis-Stegun bound, and this is by Banks, Moore, Neiman, Metropoli, and Abe and Sandin. Also, in the disordered case where A is less than B, there is an explicit expression for the information theoretic threshold by these two papers by Koja, Allan, et al. So the new result is establishing impossibility result for 3 and 4 communities. So we show that there exists D0, a universal constant, such that if the degree is large enough and the SNR is less than or equal to 1, then the weak recovery is information theoretically impossible. That is to say, no algorithm can do better than random below the KS bound, Castanis-Stegun bound. So when Q is equal to 4, large enough D is necessary, as seen by the prior result by Abe and Sandin. For Q equals 3, D large enough is just the artifact of our proof, and for D small, it's still open, which is a nice problem. Our proof is based on analyzing the phase transition of the Potts model on a random tree, which I'll come back to in a moment. So how do we show the impossibility of the result like this? So say we have a stochastic block model like this. So we analyze the local structure of the network. So we wish to show that below the so-called Castanis-Stegun bound, we cannot do better than random. So doing a weak recovery is equivalent to saying, given two vertices, figure out if they're in the same community or not. So these, say we have access to additional information. Say we know that one vertex is colored blue, and also we have access to the information of the suppose we look at the finite neighborhood of this green vertex, and then we reveal the states of the boundary of that neighborhood. So this will only give additional information. It will only make the weak recovery easier. So it suffices to show that even with this information, we cannot recover the state of the green vertex. One can ask, what does this local neighborhood look like? Well, it turns out that it looks like the locally Galton-Watson branching process. So Galton-Watson process is just for every vertex, we have there's a Poisson number of children, and then it branches out independently. And this neighborhood can be described in terms of what's called the broadcasting on general trees. So this broadcast process can be described in general as follows. So take a tree T, and lambda is some value between -1/q minus 1 and 1. And suppose we color the root uniformly at random from 1 to q with probability 1/q. And then at each time, independently copy the color of the parent with probability 1 plus q minus 1 times lambda over q, or you flip the color uniformly. That is to say, the other colors gets probability 1 minus lambda over Q. And this is repeatedly broadcasted down the tree for each vertex. And in fact, we verify that a neighborhood of the block model can be coupled with a broadcast model on a Galton-Watson tree with Poisson D offspring distribution. And lambda encodes the second eigenvalue of this process. So if you look at the transition matrix of this Markov process, lambda is the second eigenvalue. And for the block model is given by A minus B times A plus Q minus 1 times B. So SNR, which is equal to A minus B square divided by Q times A plus Q minus 1 times B, this is just the D lambda square. And D lambda square equals to 1 is what's called the Kestenstiegen bound. So in order to show impossibility result below the Kestenstiegen bound, it suffices to show that given the states of the leaves, can we reconstruct the root better than random? And it suffices to show we cannot do that when Q is 3 or 4. So if you can do better than random, we say that the model has reconstruction, and otherwise we say that the model has non-reconstruction. This reconstruction problem has many equivalent formulations and can be thought of a problem in the theory of Gibbs measures. So the broadcast model on T is just a Potts model with free boundary condition. So usually in the Potts model, there is a inverse temperature beta, and one can write out the explicit relationship between beta and lambda, just a different parameterization. And if one think of this way, then the non-reconstruction is equivalent to saying that the free measure of the Potts model is extremal. So extremal means that there's no convex combination of the Gibbs measure that gives rise to free measure. And this is also equivalent to the tail sigma algebra of this process being trivial. Okay. And besides the interest from the study of block model, this reconstruction problem is closely related to the mixing of Glauber dynamics and also clustering of random constraint satisfaction problems. So because of this, there has been a lot of interest within mathematics community to show different aspects of this reconstruction problem. So if the first result is by Kesten and Stegom in 1966, they show that if d lambda square is greater than 1, then the reconstruction problem is solvable with high probability just by a majority vote. That is to say, if one outputs what's the most popular color in the leaves, and then output that as my estimator of the root, then if d lambda square is greater than 1, then this has a non-trivial correlation with a root. So impossibility result was established much later. So for Q equals 2, it turns out that the KS bound is tight for reconstruction for any tree T. So below the KS bound, one cannot hope there is always non-reconstruction, and this was established by a series of papers. Also, for when T is a D-area tree, it's known that when Q equals 3 and the degree is large enough, the Kesten-Stegom bound is tight for reconstruction, while for Q greater or equal to 5, the KS bound is never tight. This is by Sly. So our impossibility result for the block model is based on this impossibility result for the broadcast model, which is new. So we consider the broadcast model with second eigenvalue lambda on a Galton-Watson tree T with sufficiently concentrated offspring distribution with mean B. Then we show for when Q equals 3 and the degree is large enough, then there's non-reconstruction almost surely below the KS bound. Okay, this is a generalization of Sly's result to the case where T is a Galton-Watson tree. The most interesting case is where Q equals 4, which is the critical case. And this is new even for the Dairy tree case. We show that the same holds if the degree is large enough. We show that the KS bound is tight. Furthermore, we show that there is an explicit D star such that if D is less than D star and if lambda is negative, then the KS bound is not tight. Finally, we show that when Q is greater or equal to 5, the KS bound is never tight. And D star here above matches the physics conjecture from the paper Ricci-Terzaghi, Semerjian, and Zabarova. And in particular, it is conjecture that if D is greater than D star, then the KS bound is tight. So I'll end with some open problems. So the first problem one can think of is that what's the information theoretic threshold for weak recovery and detection when A is greater than B? So in the dis-assortative case where A is less than B, this was established by Allan et al. In the assortative case, there was recently a partial result by Dominguez and Murat. Also, one can ask about signature of computational hardness below the KS bound. And recently, low degree hardness for detection problem was established by Bandaria, Banks, Koninsky, Moore, and Wayne. Also, one can analyze more general models, such as block model with partial information, and also when there's so-called the random geometric graphs, when what you're planting has some geometry. Thank you for listening.